Today we are going to discuss the BCD arithmetic, the program which is required for the arithmetic operation to be done on the BCD numbers. Now the basic operation which can be performed on the BCD numbers are the addition as well as the subtraction process. Then how this BCD addition and the BCD subtraction will be done, we will discuss in this video right now. So we know that BCD numbers are those numbers which is called binary coded decimal, which starts from 0 to 9 and there is no scope after 9. So the maximum limit is there are 10 numbers in that. So anything which is more than 9 has to be bifurcated into two parts, then only it can be represented in the BCD form. So when we talk about the BCD addition process, in which the addition is done as the normal binary numbers are being added, but the best way to understand the addition process with the BCD numbers by considering a particular case, because there are three certain cases which can happen, and depending upon those cases we will be solving the problem of BCD addition. So first case is whenever we are going to add two BCD numbers, there is a possibility. The first possibility is sum is equal to 9, means decimal 9, or less than 9, and there is no carry at all. For example, suppose we have to add two numbers 6 and 3 and both the numbers are BCD. So what we will do, we will convert this 6 into the binary number, 3 into the binary number, and when it is added, so 6 plus 3 it is decimal 9, and the result will also be in the form of a decimal 9. So this is simply normal binary addition whatever we are going to do, but if sum is equals to 9 or less than 9, then we have not to worry. The result whatever we are getting after the addition of two BCD numbers, it will be in the BCD form. But if the case 2, let us discuss the case 2, it may be possible that whenever we are going to add two BCD numbers, the case 2 is sum may be greater than 9 and there is no carry generated. For example, I have taken an example of 6 and 8. 6 and 8 is being added in the form of a decimal, the result will be 14. But whenever it is converted into a binary number and when it is being added, so the binary representation of 6 is 0 1 1 0 and the binary representation of 8 is 1 0 0 0. So whenever we are going to add, we are getting 1 1 1 0. That will be representing E in the hexadecimal form, and there is no scope of E. So whatever number we are getting, it is invalid BCD number. So if the number is more than decimal 9, if the result is more than decimal 9, the result which we are getting is incorrect BCD number. So if it is incorrect BCD number, so as per the rule of BCD addition says that if we are getting the result after adding two BCD numbers, if we are getting the result which is more than decimal 9, what we have to do? We have to add decimal 6 into that. And when decimal 6 is being added, then after addition of that decimal 6, whatever result we will be getting, that will be in the correct BCD form. So the sum which we are getting is in this example is 1110. But this is not a BCD number, correct BCD form. So what we will do, we will add decimal 6 into that. So 1110, it is being added with 0110, which is equivalent to decimal 6, and then whatever result we are getting, it is 0001 and 0100. So after the addition of decimal 6 in the lower nibble case, there is a possibility that carry is generated, and if carry is generated, that will be considered as a upper nibble, that is the 4-bit number, and it will be represented by 0001. So actually whenever we are adding 6 and 8, we are getting 14. So 4 should be considered separate, 1 should be considered as separate. So the final result which we are getting is 0001, which is representing 1 of 14, and 0100, which is representing 4 of 14. So this value which we are getting now is in the correct form, correct BCD form. Now the third case may be that the sum which we are going to do for after the addition of two BCD number, there is a possibility that the sum will be more than decimal 9, as well as there is a possibility that we are getting carry out of that. So for that I have taken an example that we are going to add two numbers 8 and 9. So of course whenever 8 and 9 is being added, we will be getting 17. But whenever it is being done by the processor, 8 is being converted into a binary, that is 1000, and 9 will convert it, it will be 1001, and whenever we are adding it, we are getting 0001 and 0001. So this most significant nibble, the higher nibble 0001, it is the actually which is carry, it has been obtained just because of carry is generated by adding the lower nibble, that is 100 and 1001. So again this value which we are getting, it seems that it is BCD, it is correct BCD, but it is not in the correct form, because the sum which we are getting after doing the addition of 8 and 9, it is 17, which is more than decimal 9. So this result which we are getting is not correct, not in correct BCD form. So we have to do some adjustment, and we have to add decimal 6 in the lower nibble for making the adjustment and converting it into the BCD form. So whatever result we are getting, we are adding 010, that is decimal 6 into that, and then whatever result we are getting, that is equal to 0001 and 0111. Now you see, when 8 and 9 is being added, it is 17. So whenever we are talking about BCD number, one will be considered, one of the 17 will be considered as a separate, and 7 of the 17 will be considered as separate, and the final result after adding the decimal 6 in the final result is 0001, which is representing decimal 1, and 0111, which is representing 7. So this number now is in the correct BCD form. So meaning thereby, what we have to do whenever we are doing BCD addition, whatever the case may be, whether the result is less than 9, then if the result is equal to 9 or less than 9, we have to do nothing. But if the result is more than 9, whether carry is generated or not generated, ultimately we have to add decimal 6 into the lower nibble, and if there is a carry which is being generated just because of addition of decimal 6, it will be adjusted in the most significant nibble, that is the higher nibble. So with these cases which we have discussed, the summary can be obtained in such a manner that whenever we have to add two BCD numbers, we do the normal addition process whatever we used to do, and if the sum is less than 9, then we have not to worry, because what if sum is equal to 9 or less than 9, it means it is in the correct form. But whenever 4-bit sum is greater than 9, whether carry is generated or not generated, we have to do some adjustment by adding decimal 6 into that. So this addition of decimal 6 can be obtained. We have a facility in 8085 to add decimal 6 by using a certain instruction which is allowed in case of 8085. However, 8085 is very much restricted by number of instructions available, but fortunately we have an instruction called decimal adjust accumulator. In the short form, it is called DA instruction, which do very meticulously the adjustment by adding decimal 6 into the result which is not in a BCD form. So let us first discuss the instruction which is used in the 8085 for making the adjustment of numbers which is not in the BCD form into a number which is really a BCD number. So as we know that in 8085 we have an 8-bit flag register, and out of that 8-bit flag register, 5 flags are being used and the rest 3 bits remains unused. And till now we have very much familiar with the different flags which we have used for the arithmetic and the logical operation, taking the decision based on the status of the result, that is 0 flag, carry flag, parity flag, sign flag. But we have still not used auxiliary carry flag, and even any user cannot check the status of the auxiliary carry flag, because auxiliary carry flag is a kind of a flag which is used internally by the processor to check whether the number which has been added in the form of a 4-bit number, whether it has become more than decimal 9 or not. So it is the property of the auxiliary carry flag to sense whether the decimal the result is more than decimal 9 or not, and with the help of that this DA instruction works. So what it used to do, it senses that whenever the result which we are getting after adding 2 BCD number and we are getting more than decimal 9, auxiliary carry flag used to set. So whenever auxiliary carry flag is used to set, it is the microprocessor which can check it whether it has been set or not, and depending upon that it takes the decision. So it is the die instruction, which is a single byte instruction, and the purpose of die instruction is to adjust the number, the result which has been obtained in the accumulator, if it is more than decimal 9, to sense by sensing the auxiliary carry flag, and if it is so, it automatically adds decimal 6 to that number. So it uses both the flags, carry flag as well as the auxiliary carry flag. And due to the instruction, all the flags are going to be affected after it is being executed. So now let us check the implementation, how the die instruction will be used if the result which is coming, which is not in a BCD form, how we can use die instruction to make the result in a correct BCD form. So we have a problem statement like write a program to add 2 BCD numbers, and the problem statement is that we have to add 2 BCD numbers, and these 2 BCD numbers are available in a particular memory location 2200 and 2201, and we have to store the result after doing the addition, correct result in the correct BCD form in at 2300. So I have taken an example in which 2200 is having first BCD number, that is 39, 2201 is having BCD number as 45, and the result which has to be stored is 20 at 2300. So whenever we are adding 39 and 45, the result will be 7e, because whenever we are adding 9 and 5, it is equal to 14, and 14 in the hexadecimal form, it is equal to e, and when 3 and 4 will be added, it will be 7. So the first 4 digits, when 9 is being added with the 5, the result becomes 14, which is more than decimal 9. So what we have to do? We have to do some adjustment, and how this adjustment will be done? By adding decimal 6. So that is why 7e plus 6 has been added, so that when you add e and 6, you will be getting 4, and there will be a carry, so it will become 84. So actual result after addition of 39 and 45 will be 7e, but we want it to be in the BCD form, so we have to add decimal 6, so that with the result will be 84. So this is how we work. So the program is very simple. The program is to initialize the counter where the BCD number is available, and we copy the first number, that is 39, into the accumulator, and then we increment the content of HL pair so that it will become 2201. So 2201 content will be added with the content of accumulator with the help of add m instruction. Add m instruction. The purpose of using add m instruction is to add the content of 2201 with the content of, actually add m, how it works? It is going to add the content of memory location whose address is present in the HL pair, and the address in the HL pair before add m instruction is 2201. So content of 2201 will be added with the content of accumulator, and the result will be stored in the accumulator. Now the next instruction is add m. Add m, after add m instruction, there is an instruction da. Now whenever we are adding the content of 2201 with the content of 2200, and the content of 2200 is available in the accumulator, and the content of memory is available at 2201, when these two numbers are added, it may be possible that the result which is stored in the accumulator may not be in the correct BCD form. So for that we have to do adjustment, and that adjustment can be done with the help of die instruction. Now the purpose of using the die instruction, the purpose of using die instruction is to convert the result into a valid BCD, because before that the result we will be getting is 7e. We are getting 7e. See, 7e. So this result is not in a correct BCD form. So we have to add decimal 6, and for that we have used die instruction, which converts the number into valid BCD. So whenever it converts the number into a valid BCD, that BCD number will be stored in the accumulator, and then with the help of STA instruction, which means store the content of accumulator to a certain memory location, and the result is required to be stored at 2300. So the result will be stored at 2300, and the program is going to halt. So meaning thereby, whenever we are getting the result which is not in a BCD form, and whenever you have to convert that result into a correct BCD form manually with what we know, we have to add decimal 6, and decimal 6 can be added by different instructions, but 8085 provides a facility of die instruction which automatically senses the auxiliary carry flag status and adds decimal 6. There is no requirement of putting another instruction by which you are going to add decimal 6. It is the duty of the DA instruction to add decimal 6 by sensing the auxiliary carry flag if the sum is more than 8 bit, if the sum is more than decimal 9. Now, let us take another example that we have to add 4 digit BCD number, and so 4 digit BCD number means pair register will be used to store. So, one 4 bit BCD number is available in HL pair, and another BCD number 4 bit digit BCD number is available in DE pair, and we have to store the result at a certain memory location, which will also be a 16 bit. So, 2 memory location will be required to store the result. So, the sample I have taken an example. First we will explain the example and then we will come to the program. So, the sample is suppose HL pair is already loaded with 3629 4 digit BCD number, DE pair is also loaded with 4738, and we have to add these two BCD numbers and get the result in the correct BCD form. So, first of all what we will do, we will take the lower digits, lower bits, lower register content, and then we add. So, how we will do? We have to add L and E register content. So, L register mein it is already having 29 and E register is having 38. So, when 29 and 38 is added, it will be actually coming 61. But 61 is not the correct value, because whenever you are adding 9 and 8 of 29 and 38, whenever you are adding 9 and 8, it will be 17, and 17 is more than decimal 9. So, whenever you are getting more than decimal 9, you have to add decimal 6. So, whatever result we are getting as 61, we have to add decimal 6 into that, so that it will become 67. Now, 67 is the correct value. Now, after adding the L register content and E register content, what we will do? We will add H register content and D register content. But one thing we have to be very clear, whenever we are adding L register content with E register content, and if the sum is more than 8 bit, sum is more than decimal 9, we are doing an addition of another addition, that is decimal 6 into that. So, it may be possible that due to LSB addition and doing the adjustment with the help of DA instruction, there is a possibility that the carry will be generated due to this, and if carry is generated, it will be adjusted in the more significant bits. So, now we are adding most significant bits of H pair and D pair. So, what we have done, H is having 36 and D is having 47, and we have added 36 with 47 plus 0. Now, here whenever in step number 1 I have added 29 with 38, the result was 61, and then it is added with 06, so the result is 67, no carry is generated. So, that is why considering that the LSB has not generated any carry, so what we are doing, we are adding the content of H register, which is 36, content of D register, which is 47, and since LSB has not generated the carry, so it will add 0. So, the result which we will be getting will be 70. Now, 70 is not in a correct BCD form. So, what we will do? We will add decimal 6. So, whenever we are adding decimal 6, the result will be 83. So, the final result will be 8367 in the correct BCD form. So, the program which is written, first of all we will copy the same way the sample program has been written in step number 1 and step number 2, the same way the program will be written. So, first of all L register content will be copied in A accumulator, and then we will add the content of E with the content of accumulator, and whatever result is getting we will do the adjustment, and after doing the adjustment we will store the result in the 230 at a certain memory location. Now, again we will copy the higher bits lenge, so H is copied in accumulator, and then instead of using add instruction, we have used ADC instruction. Now, what is ADC instruction? It is the instruction which is used to add the content of D with the content of A along with the carry flag status, meaning thereby if the carry flag status has become 1 just because of the DA instruction which is used in the line number 3, if it is so, then what we will do, we are adding the content of D register with the content of accumulator along with the status of carry flag. If the carry flag status is 0, we will add 0. If the carry flag status is 1, we will add 1. So, After doing that, again we have to make the adjustment by using die instruction, and after doing that adjustment we will store the result will be available in the of course in the accumulator. We will copy the content of accumulator to the certain memory location, that is 2301. So by this we are coming into the end of the program. So the programs are very simple, just give a time to understand. Now BCD subtraction. The way we are doing the BCD addition, there is a different way of doing the subtraction. Of course, we have used die instruction to make the adjustment in the case of BCD addition process. That same instruction can be used also in BCD subtraction. Die instruction can be used, but we have to see that subtraction can be done with the help of hundreds complement and for the tens complement. And what is hundreds complement and the tens complement? It is very simple, because normally subtraction is being done with the help of this complement method. So 100 complements is nothing but we take the 99's complement and then add 1. If we have to take 10's complement, we take the 9's complement and add 1. Now what is the meaning of 99's complement? Any number for which we want to take its 99 complement. So what we will do, we will subtract that number from the 99. Whatever is the result, that will be the 99's complement of that number. For example, if suppose we have to find out the 99's complement of 55. So what will be the value? We will subtract that 55 from 99, so that you will be getting 4 and 4, 44. So 44 is the 99's complement of 55. But if we have to get hundreds complement of 55, so what we will add 1, so that it will become 45. Similarly, whenever we have to get the tens complement, suppose we have to take the tens complement of 7. So what we will do, we will subtract 7 from the 9, so that we will be getting 2, and then we will add 1, so that the result will be 3. So tens complement of 7 is 3. The same way we do. Now let us discuss the program which is used for the subtraction of two BCD numbers. Of course, it is stored that two BCD numbers are available in E register and D register. One thing I want to clear here, that we have two values while doing the subtraction. The first value is called subtrahend. The number which has to be subtracted is called subtrahend, and the number from which it has to be subtracted is called manuend. So what we will do, so the number is available in E register and D register, it is given in the problem, and E register content has to be subtracted from D register. So the number which has to be subtracted, it will take, first we will take the hundreds complement of that number, and then what we will do, we will add the hundreds complement of the number which has to be subtracted, and we have to add that number with the number from which it has to be subtracted. And then after doing the addition, since we are doing addition, the result we will be getting, it may be possible that the result which we are getting is not in a BCD form. So we will use the instruction and can obtain the actual result. So first of all, since we have to take the hundreds complement, so accumulator is loaded by 99, and the number which has to be subtracted, which is available in E, is subtracted from that. Suppose the number is 55. So whenever we are using sub E, it means E will be having 55. So it is subtracted from 99. So it will become 45. It will become 44. And then we will take the hundreds complement. So we will increment the content of accumulator, so that it will become 45. And then this 45 number, 45 value is the hundreds complement of 55, which has to be subtracted from the register D content. So what we will do, we will add this hundreds complement value into the content of D. So what we have done, add D. So what this will do, it will add the content of D with the content of accumulator. And what is the content of accumulator? It is the hundreds complement of the number which is available in E register. And after doing the addition, we do the adjustment by using the die instruction. It will be adjusting the BCD number, and we will going to halt the program. So in this way, the subtraction of BCD is being done. BCD numbers are being done. Thank you.